Aveslu de microfoon, Barışar.
Okay, this is good. Now we're better. So let's assume that we are given a linear transformation on x, y, z such that this is equal to 1, 1, 1, 1 minus 1, 2, 1, 0, 3, and this is applied on the x, y, z. Now the question is find. So if we are given such a linear transformation, the question could be the following: find the inverse. Find the inverse linear transformation. In this case, so that's the question. Done. Now the way to approach to this problem is the following. We are given the matrix A. Okay. So finding A inverse is the solution to determining what is the T inverse. Okay. So we are given A, we need to find the A inverse. How do we do that? We know how to do it by augmenting a matrix A with an identity matrix, and then this would be the following. We have here 1, 1, 1, 1 minus 1, 0, 1, 2, 3, and this is 1, 0, 0, 0, 1, 0, 0, 0, 1. And we want to obtain on this side the identity matrix, and immediately on the other side we get the inverse A. So if we continue this one to do this step by step, the first step could be subtracting from the second row. We subtract the first one, so here we get 1 minus 1, 0, minus 1 minus 1 minus 2, minus 1, this is 0, 1, 2. Then immediately this is going to be second row minus the first, minus 1, 1, 0, minus 1, 0, 1. Okay? Then the next step could be to exchange with wait a second, or we can divide the second row by 2. So here we can get minus 2, this becomes minus 1. Minus 0.5, this is minus 0.5, and here we get 0.5, okay? The first row, it has not changed yet, 1, 1, 0, 0. Then the next step could be to multiply by minus 1. So this becomes minus, plus, plus, minus. Then from the third row, we can subtract the second row. So this becomes 0, 0, 1.5, and so this is the 1.5. Here we have minus 1, minus 1.5, minus 1.5. This is 0.5, 1, and this remains as 0, 1, 0.5, 0.5, minus 0.5. 0. The next step, we can divide by 3 over 2, so this can become, this becomes 1, the rest becomes, so we can divide by 1.5. If we multiply only the third row with this, and yeah, so if we continue like this, in the end, we can obtain that the A inverse, so if we skip a couple of steps, we can get that A inverse is equal to 1 over 9 times 333. Okay, 5 minus 4 minus 1. 5 minus 4 minus 1, 1 minus 2. Okay. So if this is the inverse, then we can say that the inverse linear transformation, it can be written as so we are from the domain of x, y, z, then the inverse T inverse would be applied on u, v, w, And if we apply this on UVW, the answer is going to be as follows. So this is going to be 1 over 9 times 3. So we can do actually this U over 3 plus 5 over 9, because we have this 5 over 9 V, plus 1 over 9 W. Then the second row would be, again, U over 3 minus 4 over 9V minus 4 over 9V plus W. No, plus 1 over 9 W. The third representation of this linear transformation is going to be again 1/3 of U over 3 minus 1 over 9V minus 2 over 9W minus 2 over 9W. Okay, so this is the inverse linear transformation T, which we find it this way. Okay. Okay, we can solve a couple of more examples, but let's move to a new approach. So we're going to talk about the range and the null space. So actually, regarding the matrices, we know that every matrix, it has the so matrices, they do have a range and a null space, right? So what this means, what we mean here is that in principle, we have a domain from where we obtain the vectors over which we multiply the matrix, right? This is the domain. Any point in this domain, which would be, let's pick this point. This point is what? It's a vector whose coordinates represent this point. Now, we apply a matrix A on points that we can determine in this domain, okay, and then all the range that we come here, this would be the range. So the range is the union of all the points which are obtained after we apply the matrix A. So this much we do remember. And the null space, it's probably a smaller domain, smaller than the whole range, because it's going, actually the null space, it's located here. It's located here, and it is, let's assume that this is the null space of A, and all of these, they go to the 0, okay? So it looks like the range is on this domain, and the null is in this domain. And with this, I mean the following. Imagine for a moment that matrix A, it's 3 by 4. It is always the best to write down the dimensions of the matrix A, and then we can also notice for a moment, so what should be X? If it is a vector, it could even be a matrix, but this would be 4 by 1, and the answer is going to be a vector B, which is 3 by 1. At this moment, it looks like the B is in the range of A, so range is a subset of R3, right? And what about the null space? Null space is a subset of R to the power 4. So it is very useful. Always you can just write a matrix which is not a square matrix, and just to remind yourself where, in which domain we are. And they don't have to be on the same subsets of the same R, depending whether the matrix is square or not. But I've noticed sometimes in the assignment and in the midterm that when you are asked to find the null space, you have found the null space of R cubed while it should have been R fourth, okay? Because you have to carefully notice the where, for what space we are talking about. Now, let's provide here a definition. So for any linear transformation from V to W, then we can say the following: the RT, so the range of this linear transformation T, it is defined such that T is applied on a vector V, where vectors V, they are a subset of this vector space, large V again. And the null space, so we just want to say that the null space of linear transformations, they are all the vectors which belong to the vector space V, such that the TV is equal to the zero vector. So far, we don't have a very fundamental new definition. But what we can say is that this RT is in fact, or the range of linear transformation T, would be equal to the range of the matrix A, which represents the T. And the null space of T, of the linear transformation, is also equal to the null space of A. So, as a final reminder, just have a look for a moment how the matrix A could be a well-structured matrix as where these are separated, but the linear transformation, it has elements only on the rows. So this was just a reminder that the null spaces are the same, and well, let's also do this one. Let's assume we have a linear transformation which goes from R squared to R4, and this is represented by taking a pair of numbers, x, y, into a quadruplet combination. So we have, let's say, x plus y, y, x minus y, and y. So what this would be? This would be the grades of two students. So we want to find what is the sum of the grades of two students, what is the grade of the second student, what is the difference between the grades of two students and the grade of the second student. So in principle, this is just 2 by 1. It's projected into a new domain, into a new range, which is 4 by 1. So this means that the matrix S, it should be a matrix which is 4 by 2 times a vector x, which is 2 by 1, and this is the only way for us to get the 4 by 1, right? So here we can immediately try to determine what is the dimension of the matrix which is going to represent the linear transformation. So now we can also find out that this matrix A, which is 4 by 2, it is going to be equal to 1, 1, 0, 1, 1 minus 1, and 0, 1 again. Again, this is 4 by 2, everything matches. And we know also that so what is the range of A in this case? We know, so let's ask this question. What is the range of A? Now, the range of A, we know that it is a linear combination of the columns of A. So it's going to be C1 times 1, 0, 1, 0 plus C2 times 1, 1 minus 1, 1. Okay? And what is the dimension of the range of A? It looks like the dimension of the range of A is simply equal to 2, right? Dimension of the range of A, it's equal to 2, because it's composed of two vectors. Now, what can you say about the null space of A? We want, so the null space of A, if we have a look back here, no, where is the best? Okay, so the null space, it should be, so range of A, it is a subset of R4, right? So we should not forget this. And the null space of A is a subset of what? Of R squared, because we know that the null, we pick it from here, and the range, it should be projected into here. And the question is, what is the null space of A? This means that we have to solve this equation, which is the following. So I don't want to write a lot of things, but this means that we have to have here x, y, and this is ax, and this should be equal to what? 0, 0, 0, 0. We know how, so this would be, if we look just at the part in blue, that means that we want to find the null space of A, okay? There is some overlap between the previous information and now, but let's see what we get here. From the first equation, we get x plus y, this is 0. The second equation, we get y is equal to 0. If this is true, then this is 0, 0. We get that the null space of A is what? It's just the origin of the two-dimensional Cartesian coordinate system. Now, with this discussion, well, we have seen before the rank nullity theorem, and the rank nullity theorem, I think is going to be equivalent to what we have seen before in the rank nullity theorem for the matrices. And here we can say that for any linear transformation P, which goes from V to W, then the rank of the linear transformation T plus the nullity of T, this is equal to the dimension of V, okay? Now, how can we see this problem again? Now, what was V? V is the vector over which a matrix, we always go back to the 4 by 7, okay? What is this vector here? This vector here is 7 by 1, we should get the V, which is 4 by 1. Now, once you write this one on the side of your exam paper, just so that you don't make a very stupid mistake, you see now what we are talking about. So it looks like the rank of T, which in this case would be corresponding to the rank of A, plus the nullity of T, which means that what would be the dimension of these vectors. So these vectors which belong to R7, what is the dimension of the nullity? It's equal to the number of vectors whose linear combination construct the null space, okay? For the moment, the vectors here, they belong to R7 for sure, okay? Because you need 7 numbers to represent them. But probably the null space of this equation could be represented by only 2 vectors. Then that makes the dimension of the null space being 2, and this would be 2 plus the rank of A. We'll get the dimension of V, and the dimension of V. What is the dimension of V? Can somebody answer this? This is just a representative example. Try to understand the general expression here. What is the dimension of V here for this example?
4.
V is over which the linear transformation is applied, so it is 7. Okay? Because if we see here, we are applying the V is where we apply the initial transformation, right? And we are projected onto the W. So dimension of V would be the 7 here, okay? Is it clear? Okay. So this is the rank nullity theorem for the linear transformations. Okay. Now, we're going to solve a couple of examples with the rank nullity theorem, but next, let's jump to the coordinate change. So, what is the coordinate change? Now, we know that if we have any, let me see what notation I have used here. So I have used notation x. So for any vector x, which can be expressed in the standard basis, the coordinates of x, we are going to represent them like this, okay? So this means that this would be the coordinates of x in the standard basis. But we can also represent the whole vector x in a completely different domain or in a different basis. So we can also write this one as the projection of vector x on a vector on another basis s. Now this is what we're going to see next. And regarding this, let me see how we can formulate this the best. Standard basis x and 1. Okay. Now, actually, the formal definition it takes some statements on the board. Let's assume that the vector x can be represented as a linear combination of several vectors vi. Okay, so let's do it like this. And these vectors vi is not the standard basis itself. And then, if this is true, then we say that this vector x in the standard basis b. So this means that these are the coordinates. This would be alpha 1, alpha 2, and alpha m, or would be simply reported as alpha, or we can look at these like this, and again we denote this as b. Now, at the same time, now this representation here, the way that we can see this is the following: that this vector x, this is equal to the linear, so we see that this is a linear combination of several columns. If we have here column v1, or vector v1, v2, and vn, and we multiply this with alpha 1, alpha 2, alpha m, in principle, these two expressions are equivalent to each other, okay? So they're the same, because we are multiplying all columns and we are obtaining is the same way as we're trying to identify the range of this matrix, which is composed of these vectors, okay? So using the same notation, and this would be, in fact, we can denote here a matrix P, okay? And this would be the coordinates, which is the projection of the vector x in a basis B. And this is, let me call this one, this is the standard basis. What was the standard basis? It was simply the XYZ or the orthogonal coordinate systems. Now, with all of these that we have on the board, I believe that the best thing is to start and offer an example. But for the moment, from what we see on the board, we have that x in the standard basis is equal to P, matrix P, times the coordinates in this basis B. The question is, how can we find the coordinates of this vector B in this new domain? This would be the question, and this would be equal to P inverse times the vector X, okay? Everything we'll try to make it clear soon. Okay, let's solve an example. Now, it is my objective to make this change of basis examples the most beautiful topic to all of us, and because it is very essential. Now, just a small reminder: the standard basis is the, let's say, the vector 311. Okay, it is always in standard basis. But let this example do the talking. Sorry. So let's look at three vectors: 1, 2, minus 1, 2, minus 1, 4, and 3, 2, 1. Okay. So the question is, could this be a basis for R3? What do we do for this? So the question is this: is this a basis for? This is the question. Now we say that we are given three vectors, and we are asked whether this can cover for R cubed. What could we do? If it is 3, then we wish all of these three vectors to be linearly independent of each other. How do we check that? The first thing that we can do, the simplest thing, is to check for the determinant. Okay. Then, if we calculate the determinant, we get a 4. If the determinant is equal to 4, we say that this is different from 0. So they are all linearly independent. Okay. So if it is different from 0, this implies that they are linearly independent. Okay. If they are linearly independent, we say yes, they constitute a basis. So this means that these three vectors, they can constitute a basis, which means that we can project any vector onto this new basis. Or we can write any vector as a linear combination of these three vectors. Okay, this is an equivalent way of reporting this. Okay, so based on what we wrote here, I can even continue here like this. So, кто векторът целят до шпигонен не вектор x и вендосим си колонът ексаматрицис p. So here we'll have here 1, 2, minus 1, 1, 2, minus 1, first column, the second one is 2, minus 1, 4, and 3, 2, 1. Okay, that's good. So this is our new matrix P. And we are getting this information from the formal definition we gave before a while. And let's see, for example, the example goes as follows. If we have a vector v, okay, such that such that V in this basis it's equal to 4, 1, minus 5. So if we have the vector V such that it's equal to the projection here is 4, 1, minus 5, the question is the following: what is V in the standard basis? Okay. Let's try to identify it. So these 4, 1, minus 5, they are these alphas, right? And these alphas are alpha 1 times V1 plus alpha 2 times V2 plus alpha 3 times V3. So as a reminder, let's try to remember that this is alpha 1, alpha 2, and alpha 3 in a basis B. Basis B is this one, this is V1, V2, and V3. So let's write them here. This is V1, V2, and V3. So then V itself, now we're writing V in a different way, would be equal to alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3, which means it's equal to 4 times 1 to minus 1, then plus 1 times 2 minus 1, 4, minus 5, what is this? 3 to 1, 3 to 1. Okay, so it looks like this vector whose projection on this basis with these coordinates is going to be the following. So we get here 4 plus 2, 6, 6 minus 15 minus 9, 4 minus 1, 3, minus 10, minus 13, minus 4 plus 4, 0, minus 5. Okay, so apparently this vector V is the following: minus 3. This is correct. It should be, let me check again. So this is 4 minus 1, 3. 3 minus 10. No, there's something wrong. No, this is 8. 7 minus 10, this is minus 3. Okay. This is minus 3, minus 4, 4, 4, minus 5. Okay. So apparently this is the vector V. Yeah. Now the question is, so what were we given here? In this example, so far we were given. So these are two domains. The first domain is composed of basis B, which is composed of this basis 1, 2, minus 1, 2, minus 1, 4, and 3, 2, 1. Okay? So this is the basis. But this is a made-up basis. We came up with this one we wanted it this way. What is the standard basis? This is 1, 0, 0. Okay? 0, 1, 0. And 0, 0, 1. Okay, this is the standard basis. This is the B basis. What have we done so far on the board? On the board, we have a vector which is equal to 4, 1, minus 5. So we have a vector 4, 1, minus 5. Okay, this is a vector in this basis. What is this vector in this new basis? It's equal to minus 1, minus 3, minus 5, minus 9, minus 3, minus 5. Okay. So in this instance, by the way, this matrix P is this. The transformation matrix is this one, P. Okay. And let me have a look again. We used, wait a second, yes. We used matrix P to move this way. Okay, so from this basis B, so let me call this one B basis, okay, because we just called it this way. What is this? This is standard basis. So we have a basis it was a basis because the determinant of the 3 by 3 matrix, it was different from 0, then what would this be? Would come up this way. Now, we know linear algebra, we are very good at moving from one domain to the other. But how can we move backwards? How can we come from this domain to this one? We can apply an inverse matrix P inverse, okay? So, given this, let's ask another question. Let's give a vector which is 5, 7, minus 3. Okay? In fact, this is, so let me draw it like this. Now, we did it by moving this way with matrix P. What about if we give a vector as 5, 7, minus 3, 5, 7, minus 3? This is a new vector. What would be the projection of this vector here?
The inverse.
That's correct. How are we going to find it? This is going to be, you are right, we do P inverse times 5, 7, minus 3, right? And this would be the answer here. So we are going to move from, sorry, maybe this is not the best way, but we want to move it this way. So this is the question that we're going to formulate into the changing the basis from one basis to another. So the P, we know the P, okay, this is P. Now we need to find the P inverse and we multiply it. Now the P inverse is, let's see, I just need to use, so this is the B basis, we know that much, but the P inverse is equal to 1 over 4, because that's what the determinant is, minus 9, 10, 7, minus 4, 4, 4, 7, minus 6, minus 5. Okay, this is the P inverse. We multiply in the vector in the standard basis, 5, 7, minus 3, 5, 7, minus 3, and we get the vector which is 1, minus 1, 2. 1, minus 1, 2. So this vector which we did not know, okay, so this is let's say, this is how we can change from one basis to another. I mean, all the essence is now on the board. We always go from a good-looking basis, which we are used to it, to a different one. What do these vectors help us to do? To determine the P. What does the P do? The P's, they always project the vectors into the standard basis. Okay, that's why we show it like this. P sends us to the standard basis. How can we move backwards? We find a P inverse. Okay, and the question that might come to us would be the following. Okay, given this vector that looks like this on a standard basis, find it what is this way. We just multiply this one with P inverse. Or we might be given this vector, 1 minus 1, 2. What is how does this vector look in the standard basis? We do again this P times this vector, we should get 5, 7, minus 3. Okay. So, given the example, maybe it looks it's more self-explanatory than providing the whole theory. Not that the theory is delicate or difficult, but I hope we try to explain this the best way possible. Now we can come up with another examples for sure. So you may come up with 3 vectors which are linearly independent. So if we randomly generate them, 1 minus 1, 0, 5 minus 5, 7, and 2, 0, 3. So we can check the determinant. If the determinant of the 3 by 3 matrix here is different from 0, this can constitute another basis B2, and this is going to correspond to another matrix P1. Okay, and then we could ask the following question. So here we have another basis which is composed. This is basis P1, this is basis P2, whatever, and we could ask, for example, the following question. So if we have a vector x that in the basis P1, let me denote a different basis. If this is equal to 1 minus 1, 1, okay, what is this in the standard basis? Okay, this would be the question. So let's find what is this vector here. So let me add, this is 1 minus 1, 1. 1 minus 1, 1. And let's see, what is this vector here? How do we find it? We just multiply this with plus 1. We take a minus 1 here, another plus 1 here. So this means that in the basis P1, okay, so let's do this one. This would be equal in the standard basis as what? 1 minus 5 minus 4 plus 2 minus 2 minus 1 plus 5. This is 5, 4. This is 4. You can correct me if I'm wrong. This is 0, minus 7 minus 3 minus 4. So this minus 4, this is in the standard basis. Let me write this as is. We have minus 2, 4, minus 4. Minus 2, 4, minus 4. So this vector is the projection of this vector on the standard basis. Now, the question is, this vector here, in the, which is, let me call this one P1, okay? How would this vector look in this basis, okay? So we have a vector which is somewhere, and let's find what is the projection of this vector in here. How can we do it? It looks like, any solution for this? How would you answer this?
Can we turn it into the standard basis and then turn it into the basis of P?
Yes, that's true. I believe you are right. So here we have 1, minus 1, 1, okay. Let's turn this one into the standard basis. How would it look like? Me çfarë matrice duhet ta shëndzojmë këtë vektorin tonë? We have to multiply with basis P1, okay? Which is this actually, we just remove these columns, and this is P1. So this vector here, 1 minus 1, 1, we multiply with P1, then we are here. Then from this domain to go to this domain, we multiply by P inverse, right? This is it. So then, so we can use a very elegant way how to transform from one basis to another. So as a reminder, let me write this one. What was this? 1 minus 1, 0, 1 minus 1, 0. The other component was 5 minus 5, 7, 5 minus 5, 7. And then we get 2, 0, 3, 2, 0, 3. So then we know P and P1, okay, so if we know P and P1, which would be composed by these vectors as their columns, it is very easy for us, forgetting that we have the standard basis, we can forget it for a moment, and we can easily transform from here to here, okay? So what we should do, we should include multiplications that are going to look like this. P inverse times P1. Again, we know what P inverse and P1 are here, okay? So we can easily track them down. So why are we using the standard basis? We could use standard basis because it can help us to go from one, we can use it like a bridge, okay? To interconnect to different domains. Is it clear?
Yes.
Okay, that's good. Do you have any question? If you have no more questions, we can stop for today. But I really want all of you to go over chapter 7 very carefully and look at the examples, because this is the most beautiful part of linear algebra, and you can apply these solutions even when you want to solve a system not of linear equations, but even systems of differential equations, which technically they belong to a relative difficulty which look a little more difficult, more challenging. But using linear algebra, they become very trivial, very simple. Okay, so please just read them carefully from the textbook in detail. Okay, we can stop it here for today. I want to thank you for your attention.